Good morning, calculus peoples. We're going to do some problems today involving a new topic that's related to topics that we've already done, but that topic is on volume. And today we're going to use a technique that is called the washer method. My marker is getting a little dry. It's also getting even squeakier. Same squeaky one I've been using for a while. Let's do an example to start that's going to illustrate exactly what the washer method is. So we're going to start with a problem, and the problem is find the volume of the solid generated by revolving the region bounded by y equals 1 over x, y is equal to 0, x is equal to 1, and x is equal to 4, about the line y is equal to 2. All right, let's read that. There's a lot going on in that problem here. So it says we're going to find the volume. We know what volume means. It's three-dimensional space of the solid generated by revolving. That's a key word. When we revolve something around some sort of axis or whatever it is we're revolving around, we're talking about circles. The region bounded by y equals 1 over x. I know what that looks like graphically. Y equals 0, x equals 1, x equals 4, about the line y equals 2. So this is different in itself because when we use the disk method, we were revolving around the x-axis, which is actually y equals 0. So this one we're revolving around a line y equals 2. But just like the disk method, I'm going to want a sketch for this. And I'm going to tell you we're going to end up rotating kind of up. So I'm going to start my x-axis kind of low so that I have room to draw my graph rotated upwards. All right, let's try to use some colors here. All right, so I need y equals 1 over x. What does that look like? Well, that's going to look something like this. We got y equals 0. We know that's just the x-axis, but I'll label that y equals 0. I've got x equals 1. That would be over, like, I don't know, maybe I'll call that 1. And I'll do a dot up there. This is 1. And then x equals 4. So that'd be 2, 3, 4. So this is like x equals 4. And y equals 0. So this is the region we're talking about right there. So that's my region that's been bounded by those functions. We're rotating this around the line y equals 2. Well, this right here represents 1 because this is when x is 1 and 1 over 1 is 1. So there's 1. So I'm going to go up to 2 and make a mark. And so this is the line. Maybe I'll use a different color. This is the line we're rotating around, and I'm going to make a dotted line. We're rotating around this line. So we're rotating up and around. So what's that going to look like? Well, let's just try to get a diagram here of what this would look like. We're going to make circles. So I'm going to draw a radius here. And that radius needs to be the same up top as I rotate around. So I'm thinking about this point right here. And I'm just going to draw a sketch. So there is like a radii. Actually, that's a radius. Here is a second radii. If I went up this far here, this distance has to be matched up top. So maybe like that. And I'm going to draw another circle. So as we rotate here, we're looking for these distances to stay the same to get an accurate graph. So this is what the inside piece is going to look like. Okay, on the outside, I'll draw maybe a couple more in here. Boom, boom, be up a little more. And again, this is kind of what the inside is going to look like. Okay, on the outside, it is going to be just the radius, I think, is going to be the same. So I'm talking about going from 0 all the way up until 2. So I'm going to go up 2, boom, and I think that radius is going to be the same the whole time. So my circles, this is really going to create like a cylinder on the outside. So here's kind of my diagram. And I know this is going to turn into a total mess, but just trying to give you an idea what's happening here. This would rotate up And as I get more and more marker, it gets more and more messy. So let's try to draw this shape out here. A little more in the clear, and maybe I'll do it like right along here. So I'm going to do this. Here's my line y equals 2 again. And then here's my graph. And we're only going to focus on the part that we're interested in. That's a bad comparison there. So it's going to come more down and in here. So we're focusing on this region right here. So what's that going to look like? Well, on the outside, it looks like a cylinder. So here, it's going to be like a line going over here. And from the outside, this part looks like a cylinder. So on the outside, boom, we have these two ends that look like this. But what happens then, since we're revolving only this solid around there, again, I'll outline the solid and see if I can get a different color. We're outlining this solid around this. So there's going to actually be a hole in the middle. And that hole is going to look like this. Maybe be this big here. And then as I went down, let's see, it's going to look something like this. And there will be a hole in the middle. Let me draw a different sketch for that that's not on a graph. All right, so it's basically going to look like this. There'll be a cylinder on the outside. And on the inside, it's carved out. And that inside carving looks like this. It starts with a smaller circle, and it seems to go like this until it gets to the edge. And then it has an open circle right there as well. So again, from the outside, this looks like a cylinder, but the inside's got kind of like a vase that is carved out. And our goal is to find the volume of this three-dimensional solid. Well, if I turned this to the side and I looked through it, let's say we looked through this direction, what we'd see is this circle on the outside from the cylinder, and we would see this middle that's been carved out. And this, my friends, is called a washer. Why is it called a washer? Well, because it looks like a washer you put on a bolt. No other reason than that. It's not really a fancy word. Let's think about how we would find the area of this washer. So just like the disk method, what we're going to do is we're going to write functions for these circles. And we're going to integrate going across, because that is going to accumulate and put all of those circles together for us, even though they're infinitely small. That's what integration does. It's going to put all of those together. All right, so how do we find the area of that washer? Well, I'm going to draw it again right here. And basically, if I was to find this area, which I'll shade in right here, I would do the area of the big minus the area of the small. And in this case, let's do those. So what is the area of the big circle right here? Well, let's look at our circle and think about what this is. And these diagrams can get a little bit messy here. But the big circle is all the way to the outside. Remember, this is like a cylinder. So that big circle, how far is that? Well, that's a constant. It's this the whole time. So that big radius, I'm going to use a big R for that, is going to be equal to 2. So the area of this really large circle, or I'll call it area of the big, is going to be pi times 2 squared, which is going to be 4 pi. So that's the area of this outer circle. But what we need to do then is we need to subtract away this inner circle. And I'm going to call that little r. And I'll call this area of the small. And let's go ahead and look at our diagram and try to dissect what's the radius of the small. So I'm going to start right here. I'm going to draw 1 in right there. So we're looking for this distance right there. And again, on this board, it gets a little messy. It gets messy on all the boards. What is that distance? Well, that distance I'm going to represent by going up to 2. And then I need to subtract away this right here. And what is this right here? Well, it's changing every time. And how is it changing? Well, this is a function. That function is my 1 over x. So this is going to be defined as 1 over x. Depending on where the x is, that radius is going to change. It's going to be this whole 2 minus whatever this little piece is. This is this whole 2 minus whatever this little piece is. That's going to give me this radius right here. So that is going to be 2 minus 1 over x. And so therefore the area, oops, that's not the area. That's the radius. I'm going to erase this part. Little r is going to be equal to 2 minus 1 over x. And therefore the area of the small is going to be pi times 2 minus 1 over x quantity squared. Hopefully that fits on the board. I think I'm okay over there. All right, but that's not my goal. So my goal is to find the volume of this shape right here. Okay, so how are we going to do that? Well, let's write a function for the area of this washer. And the function is going to be the area of the big minus the area of the small. So the washer, I'm going to write area of the washer, is going to be 4 pi minus pi times 2 minus 1 over x quantity squared. Now remember, that is just one of the washers. Our goal is to figure out what's the volume of this. So this is going to give me a formula that's going to give me the area of any washer. So if I cut this, boom, it's going to be some sort of washer. That washer looks about like this. But what we want to do then is take every washer. And how do we do that? We're going to use this function called integration. So let's complete our problem then. So we're going to say the volume of the washer is going to be equal to the integral from, and we're going from 1 to 4, of 4 pi minus pi times 2 minus 1 over x quantity squared dx. And we got a whole bunch of mathy stuff to do here. And I could go through this and we could box method this up. Just for time's sake, I'm going to not do that. And the reason I'm not is because we're not focused on integrating right now. We're focused on conceptually how do we write integrals that will represent this volume. So you could calculator this up, whatever it is you're going to do. But one thing I want to point out here is these both have a pi. So I would actually just take that pi out, and I would have the integral from 1 to 4 of 4 minus pi times 2 minus 1 over x. No, there's no pi. I took that out. Squared dx. And then we'll integrate that, and we're going to end up with pi times 4 natural log of 4 minus 3 over 4. And that would be the volume. And if I was to put a label on that, I would say that would be cubic units right there. All right, let's do another example for this. All right, friends, we're on to our next example. But before we go on to our next example, I want to summarize our volume using the washer method. When we're using the washer method, here's how we figure out volume. Volume is going to be equal to pi times the integral from a to b, and it is going to be capital R sub x squared minus little r sub x squared dx. And this capital R sub x is the big radius, and this little r sub x is the small radius. And this really comes from the area of our washer. The area of this washer is going to be capital pi capital R squared minus pi lowercase r squared. I take out the pi out front. That's going to be one washer. We integrate across to get the volume of the whole, whatever shape it is, whatever three-dimensional shape those functions may create. All right, let's do another example here. Itchy nose. All right, so we're going to determine the volume of the solid generated by rotating the region bounded by y is equal to x squared minus 2x, and y equals x about y equals 4. All right, friends, what are we going to do first? Well, let's take it apart and make sure this question's making sense. So we're going to determine the volume. That means I know I'm talking about a three-dimensional shape of a solid generated by rotating. I know I'm talking about circles, washers, or disks. The region bounded by these two functions must bound something. I am rotating around y equals 4. Okay, so I'm going to draw a little sketch, and I'm going to draw the line y equals 4. I'm rotating around that. So this is going to be y is equal to 4. All right, we have this right here. This is definitely a parabolic function, and I'm going to tell you it looks like this. We could use our graphing calculator to do that, but here is y equals x squared minus 2x, and this right here is y equals x, and that is going to go right here, and this is y equals x. All right, so what are we doing with this? We're determining the volume of the solid generated by rotating the region bounded by these two functions. Well, let's identify the region bounded by those two functions. Well, that region is going to be right here. And I'm going to rotate this around this. Let's practice visualizing that. So I like to just draw like circles. Here's the inside. And here's the outside. Let me go up that distance. So the outside is going to look like this outside of the shape. So it's going to look like this. Let's see. Here's the end of it. Looks like this. Not the worst drawing I've ever done, but I've done better. All right. And then this is going to be a straight line right here. It's supposed to be straight. How's that? There we go. There's a massacre of a drawing. All right. Not horrible. So we can visualize that. So let's rotate it around. If you were to draw that three-dimensionally, we can imagine this board I don't think necessarily lends itself super well to drawing three-dimensional shapes like this. But it's going to look like this. It would be like a vase with the bottom opened, and then this would be like dotted down the middle. It would have like this open like cone shape inside of it. All right, that's a massacre. All right, we're going to need to know this intersection right here, and I'm going to tell you this intersects at x equals 3. We could use our calculator to figure that out, but for the purposes of this, or we could set them equal to each other, again, we're going to focus on how do we find this volume? How do we write an integral that's going to find that? All right, so we know we're going to have to figure out the area of the washer, which means we're going to have to figure out the big R, which is the big radius. All right, so what's the big radius look like? Well, the big radius, let me draw a few in. Right here would go from this right to here. All right, so we need a way to express that distance in terms of what we're given. And that big radius, and unlike our last problem, is changing every time. And let's focus on this one here. So this distance right here, I could represent by saying this all the way is 4. But I need to get rid of this part right here. And this part right here is going to be our x squared minus 2x. Again, right here, I'd have this full distance, and I'd have to subtract away this bottom one. And when I subtract away, that would actually add to my radius. So big R is going to be 4 minus this piece right here, which is represented by this parabola. And I'm going to make sure that I put that in parentheses. All right, so then, I call that f of x? No, I didn't. We'll leave it like that. Then I would have little r. And what's little r going to be? Well, little r, try to use a different color here, is going to be like this distance from here down to here. And how would I represent that? Because that distance is changing every time. Well, it's the same way. I'm going to go all the way down to the x-axis, which is a distance of 4, and I'm going to subtract out this distance, which is a distance of y equals x. So this is going to be 4 minus x. All right, so what does our washer look like? So the area of the washer is going to be pi times 4 minus x squared minus 2x squared minus pi times 4 minus x quantity squared. This is the area of one washer. My goal is to find the volume. So how are we going to write volume? Volume would be, I'm going to pull the pi's out. Now, this is one washer, so if I cut this, again, if I could take a slice out of this, boom, here's a slice, and I'm looking at this particular washer, which is right here. If I drew a circle of that, it'd look like this. Those washers are changing all the time, which is why we have to write them as functions. But they're going to have pi in each of them. So I'm going to pull pi out, and I would integrate those areas all the way across. So this is going to end up being pi times, and be careful with your parentheses on these because we want to write our mathematics correctly. So it's going to be put a bracket, and then we're going to do 4 minus x squared minus 2x quantity squared minus, we took this pi out. I'd always put this pi out front. We'd have 4 minus x quantity squared. Watch how I put the bracket there and the dx. Now be careful when you're writing these. Sometimes in the AP test, it's going to say literally write the function that represents the volume of this solid. This would be the answer, and you're done. But we need to be careful. We need to be careful with our parentheses. Because, for example, if I wrote it like this is written incorrectly. And guess how many points that's going to be worth on the AP test, even though conceptually you understand what's happening, it's going to be worth 0. Because the goal is to write the integral. So I would need to bracket all this stuff together. So long story short, just be careful when you're writing these that we're opening and closing our parentheses accordingly. All right, anywho, this is a lot of algebraic stuff. And in the end, I'm going to tell you that volume is equal to 153 pi over 5. And we're going to take it for granted. Again, what's our goals? Our goals are not necessarily to integrate. I think we need to know how to integrate something like this. We would distribute, we'd square this boxes, we'd box that. We would have all sorts of algebra from Math 2 and 3 that we would have to go through and fill up this whole board, and that we need to know how to do that, and I'm not downplaying that. But I want to focus on our goal. Our goal is writing integrals that will determine the solid, the volume of a solid generated by rotating around some sort of line. And today what we're using is the washer method. How do we use the washer method? We're going to integrate basically the big circle minus the little circle in terms of area. We're going to integrate that across this entire shape, which is a big mess because I have so many lines on there trying to make all the different points on those. Okay, here's the things that we need, the steps we need to be able to do in order to do that. Step 1, we need to be able to find the big radius. What do I mean by the big radius? I'm talking about from the inside of the shape all the way to the outside. And then we need to subtract away this hole in the middle, which means we're going to need to be able to find the little radius, and we're going to turn those into circles, and we're then going to apply the entire washer method through integration. Okay, again, your goal today is to find the volume of a solid generated by rotating around some sort of line using the washer method. And again, washer just means it's got a hole in the middle of my disk. All right, so that's all I have for washer method. Go ahead on to the classwork for today, and good luck on those problems.